Hey there, it's another edition of Kung Fu Physics. We're working our way through practice physics GRE problems. The one I have for you tonight is number 22 off of the 2001 exam. Scan the answers real quick. It's sort of a trivia-esque type of problem, so we'll have to be reading those answers and choosing the correct one. Let's go read the text. 22. An astronomer observes a very small moon orbiting a planet and measures the moon's minimum and maximum distances from the planet's center and the moon's maximum orbital speed. Which of the following cannot be calculated from these measurements? Okay, so basically we're going through the answers and checking them off one at a time. And we should be able to calculate almost all these things except one. I'll level with you. When I answered this problem, I answered this really quick and sort of just intuitively guessed the right answer to this without having to think too much about it. Hopefully you can do that too, but I'll give a little bit of commentary on these answers. So we'll start with answer A. That gives me a little bit of a question mark there. I don't know about that. So I'm going to put that in the maybe pile. Move on to answer B, the mass of the planet. And this is also related. I'm sort of looking at these answers as a whole too, by the way, as you should. The mass of the planet is I think, related to the period of an orbit. So, does the mass of the planet determine the period of an orbit? Hopefully, intuitively, you're screaming out, yes, yes, it certainly does, because if I'm setting up a spacecraft in orbit around planet Earth at some given distance r from the center of mass, and then I set up that same spacecraft around the planet Jupiter, let's say for example, at that same distance r, you gotta realize that it's a different amount of energy involved there. Jupiter has a much deeper gravitational well, much more gravitational potential energy, and so you're going to have to send that satellite that's going in an orbit, let's say a circular orbit, around Jupiter. It's going to have to be going much faster to not fall into the planet, in the case of Jupiter. Hopefully you see that. My point there is that those two are related. The mass and the period of the planet. The more massive the planet is, the faster the orbit has to be. So both of those, I sort of in my head am checking those off together, because both of those can be determined given the details that the problem has laid out for us. It's got a speed, and it's got the size of the orbit. I mean, I am not being rigorous here. I'm totally hand waving. But I mean, if you have the speed, you know, in a circular orbit, and you have a speed, and you have the size of the circle, you can easily get the period there right. Even though this isn't said to be a circular orbit, of course, you can also use Kepler's laws. Look at Kepler's laws, and you can get the period from that as well, knowing the what is Kepler's law? It's based on the semi-major axis of the orbit, which is answer E, right? So you can also get that because you have the minimum and maximum distances from the planet's center. And so if you're imagining the planet sitting at one of the foci of an ellipse, and you have those two distances to the outside, you can easily get answer E, the semi-major axis. From there, if you have the semi-major axis, you can calculate the period. The period is going to be related to the mass of the planet. The minimum speed of the moon. We know the maximum orbital speed, the minimum speed. You can also get, given all that stuff, and again, I'm not being rigorous here. I'm not going to write down and show how you would be able to get the minimum speed. It's interesting. If you're interested in it, you should get it out. And look at how you would do that problem. But Yeah, I'd have to think. I'd have to think more about how to get the minimum speed exactly, having the maximum speed and the dimensions of the ellipse. But it just seems intuitive that you can get as well. Probably from something like Kepler's law too. Probably something like Kepler's law, because it's regarding one of Kepler's laws, the one that's talking about how areas are swept out over equal time. I think you could maybe fidget with that to get the minimum speed. Anyways, long drawn out explanation and some hand waving for a problem that I answered without even thinking that much about it at all. I answered A, and so after looking at those 4 other answers, I came back to A, the mass of the moon. Now it says the planet is a very small moon, and all that's hinting at is the moon's gravity can be neglected. The moon is not pulling back on the planet. We can neglect that in the problem. So the moon is not making the planet do a little wobble, right? So it's a very small moon. And the only other example that comes to mind as far as how I guessed that and sort of intuitively knew that was the answer when I answered this problem is it's kind of the same thing as if you have some masses here on planet Earth, and say I was in a vacuum chamber and I was dropping the old physics experiment, a bowling ball and a feather in a vacuum, and they're going to accelerate at the exact same rate. And that's a consequence of the way that inertia and mass are the same thing, and it sort of extends into the realm of what we're talking about here, orbitals. It doesn't exactly matter if that small moon weighs, 5 kilograms or 10 kilograms or whatever a moon would weigh, on the order of magnitude of what a moon would weigh. The same thing goes in my head. I also sort of imagine like the space station and the space shuttle. Let's say back when the shuttle used to be going and those two would get close and they would be docking, if they shut off all their thrusters and just sat there sitting right next to each other, how would they move in their orbit? Well, they would move at the exact same speed. Somebody that was looking at that situation from the outside, knowing nothing else about the shuttle and the space station, what we know, clearly the space station is much more massive, but looking at the shuttle and the station from an exterior point of view, somebody wouldn't be able to tell what the masses of those two objects are. They're in the exact same orbit, behaving the exact same way. And that sort of was the understanding of how that worked in my head that brought me to answer that question pretty quick. And so I know I'm hand waving, and I should really do my homework more and give you a little bit more on some of these. So I may remake some of these problems and give some more detailed narration on better stuff to study on a problem like this. But for now, that's what we got. So that's number 22 off of the 2001 exam. As always, thank you for watching.